Correct.
Just need to make sure that the sound is also going to have
Heating.
yeah. So one of the first things that we noticed on campus is we were driving this morning was the bar.
Hey there.
Is that not true if I didn't just for the next hour or so, I'm happy that we'll be here to listen to Professor Ramirez tell us about some of his thoughts on bad news for unintended news. Maybe not bad news, maybe.
Overall good news. Overall good news. Overall good news.
Yeah, depends on who you ask, I guess. Anyway, so I'm very happy to have Professor Art Ramirez visit us and give the first motion with the semester. As maybe some of you graduate students have learned already, he's had an interesting trajectory professionally. We started off after his degree, started off at Bell Labs. Many of you may not even know what Bell Labs was. Congratulations, you're a lot younger than me. And then he's moved to Los Alamos. I hope everybody knows our physics and measurement experts. So, welcome, Art, and let's hear about Eminuscent geometrically constructed magnets.
Good. Well, thank you for having me. Thank you for the introduction and for all the good conversations we've been having so far. Is this too loud? I'm very good. Okay, good. Okay, so, oh, that's the title.
Just go anywhere on the screen. It's all my thoughts.
Oh, no, it's frozen.
Yeah.
Oh. Anyway, okay. So this, what I'm going to be presenting is a sort of a review of a lot of literature data and a synthesis of those data. But there's a lot of my own work there. But of course, not my work. It's the result of collaborations with many great people. You might recognize many of the names of the earlier era, but I just want to draw attention to Sergei Sidranov, my present theoretical colleague at Stanford, who's been really instrumental in this work. So, okay, some background. What this is all about is the ground state of the magnetic system. There are many well-known magnetic systems. You all know ferromagnets stick to your fridge. Anti-ferromagnetism is responsible for exchange bias, useful magnetic recording. Ferrimagnetism also has a moment, and that moment, while having competing sublattice and sublattices, and metamagnetism are materials that have a field that gives phase transition. And then there's critical phenomena, which of course, magnets played a central role in because the degrees of freedom are very well understood. They're both their nature and their interactions, and sort of play a central role in all of statistical mechanics. But real materials usually have some disorder. Magnets, this has led to various phenomena such as percolation physics, which governs sort of fluid flow through free-force media, also random, unfrustrated magnets. The same physics that determines how oil can sort of go through sand will determine how magnet orders if you take spin value. Maybe that's a good argument to find it in Texas to understand that better. And then there's the very well-known subject of spin glass, which was, for me, the two main figures are John Majdasz, experimentalist, and Giorgio Grisi, who just won the Nobel Prize, partly for his work in spin glass theory. And the defining phenomena is that is one of a hysteretic cusp in the magnetic susceptibility with no other dramatic features in the other thermodynamic quantities. And there was a puzzle for some time. I'm going to spend some time explaining what geometrical frustration is, as well as spin glass. So that was more or less the state of magnetism research up until the mid-1980s, when basically all fields of condensed matter changed, and basically half of everyone went into high-TC. Like many stories, it starts with high-TC, which is started by Bednorth and Miller. It shows the original resistance curve for lanthanum varying copper oxide. The transition temperature TC was already high near the existing record, but was soon increased to greater than 90 degrees, which is above liquid nitrogen. That's what sort of caused the sort of explosion, and they won the Nobel Prize really shortly after that. So, for many researchers, the surprising aspect of this discovery was the parent compound, cuprate, which is magnetic. Normally, superconductivity is anathema to magnetism, so to see superconductivity in a material that has a copper 2+, which is a magnetic ion, surprising. So this led quickly to the proposal by Phil Anderson that the mechanism for pairing was based in what we now call a quantum spin liquid. Phil's version of the quantum spin liquid he called the resonating Delmsbond model, after the notion that an electron can sometimes lower its energy by resonating or hopping between two ions, similar to the way to the popular explanation of covalent bonding that was supported by Linus Pauling. Okay, so what is this quantum spin liquid? I'm not going to spend a lot of time on it. have to know what we're talking about. And so there are many different theories of quantum spin liquids. You can't actually sort of, depict the quantum spin liquid using ink. But you can make a stab, basically a coherent superposition of a whole bunch of different two-body paired states, and that each one of these states has a complex coefficient in front of it, or the quantum mechanical many-body wave function. And this is from many people use this to show that a quantum spin liquid is from a very nice review by Savary Balance. And then, so things are going along sort of slow level, and then around 2000, a new era of QSL theories was entered. QSL was topological states with dependent anyon excitation and possible use of quantum computation. So the main players were Jekka Wang and Alexei Kitaev, and so that really boosted the excitement about quantum spin liquids, and shows just an example of how many different flavors of quantum states. Some are gaps, some are not, some have anyons, some don't, some are 2D, some are 3D, on and on. Theory for everything. So quantum spin. So this is the important part of this review and the whole field for this lecture. Savary Balance, right? But this understanding is not surprisingly QSL. Typically, only well-defined cases at T equals 0. When the temperature is sufficiently low, the quasi-particles emerging excitations of QSL become good. That was hope. And the question is it true for real systems? Okay, the experimental situation is really exploding. I can't really depict how much work there is in this field of quantum spin liquid, but you'll get a sense just by looking at these. These are all review papers. Okay? So there's just a tremendous number of materials, even a review paper written on one particular material. So there's just a tremendous lot of excitement. So we need to understand what's going on here. The first job is in order to create such a quantum coherent state, we need to suppress the classical state, right? You can't have this quantum superposition and also have it ordered at the same time. So there are two generic approaches. One I like to call tuned frustration. So you can concoct models, such as Shastri Sutherland, like my colleague at UCSC, Sharon Shastri, where you basically tune the bond so that all the spin is frustrated. I should say what frustration means, which I will in a second. And the other is the Kitaev model, which is similar in tuning nature. This is represented by this sort of diagram where the Kitaev state exists only in a very small area. More work has been done showing that there are greater regions in parameter space which support a Kitaev quantum spin liquid. But these are tuned from a material point of view, very difficult to realize. But there's this other class of materials, geometrically frustrated, which actually is a large class of materials where the frustration is built in by the nature of the primitive unit, which is a triangle. And so it's easy to see that if you have antiparamagnetic interactions between spins, it's impossible to minimize the bond between each pair simultaneously. For discussion of the presence or absence of long-range classical order, let's discuss the mean field approximation as expressed in magnetism. The ordering temperature, which is also the Weiss temperature in the mean field model, I could say that for future reference to the Weiss temperature, is linearly proportional to J, the interaction strength, the size of the degree of freedom, how big the spin is, and the number of nearest neighbors. So many of you have seen this sort of plot of 1 over, in the mean field approximation, 1 over chi goes like temperature with an offset that is representative of the temperature at which it would order if it were a perfect mean field system. So for ferromagnets, there's no problem. For antiferromagnets, you get this sort of behavior. And frustrated systems are those which are based on triangles and which show some semblance of free ion behavior to arbitrarily low temperatures. And we're going to discuss what happens at those arbitrarily low temperatures. The idea is not new. I think the first real identification of a magnetic in this by Gregory Vanier at Bell Labs, triangularizing net, and he showed two things. One, that the antiferromagnetic version of spins on a triangular lattice does not order, in contrast to the ferromagnetic case. But he also showed that there's ground state entropy. So, So anyway, so I would have taken, so after following Phil's prediction of the origin of hydrogen C, I thought to myself, well, and it was soon found out that the parent compound antimony cuprate was actually antiferromagnetic. It just hadn't been well measured at the time that hydrogen C was discovered, and so it was sort of an experimental error, if you will. But I started thinking about, this class of material that Phil was talking about. Well, is it a class? Is it definable in terms of real materials? And I found that there were a bunch of materials that had, in terms of that 1/pi curve that I saw, a large ratio of device temperature over Tc, where Tc is some arbitrary freezing temperature in glass or water. And for F greater than 10, there's been several papers by Ramirez and Anderson that show that mean field theory is about to break down. You need too many sublattices to describe any ordering process, but that's also a sign that the system is going to try to find other ways to get rid of its entropy and long-range ordering. And this led to this, one of the early sort of materials compendia of frustrated materials, and it became clear to me that, yes, they all had, just using that criterion of that F ratio, you found that all the systems were based on triangles. These are the different magnetic or mineral classes. These are pictures of the magnetic lattice. And so I define this frustration index as one way of demarcating sort of classes of materials. And so if you just focused on those materials with F greater than 10, you found also that they all had isotropic spins. And as opposed to, so a spin that can point in any direction, as opposed to a spin that can only lie in a plane, that's called an XY spin, or a spin that can only point in one direction or anti, that's called an Ising spin. So this is sort of like the cartoon of all magnetic materials. That probably represents only 1% of all magnetic materials, but the idea is that most materials have this ratio, because it's unrealistic to think that for a certain lattice, when you populate it with atoms, that the bonds are just perfectly matched to the lattice that they find themselves on, because the lattice forms at a much higher temperature. So these frustrated materials, but there are quite a few frustrated materials, and that gives us the basis for going forward. Now, I just want to say something about entropy. Characterizing non-frustrated magnets with specific entropy. Typically, if you measure specific heat, you'll find what's called a lambda anomaly, because it looks like a Greek-letter lambda, sort of, with the peak that occurs at the device temperature or the ordering temperature. And the entropy that comes out will look like this. You'll get ultimately R log 2s plus 1 with half the buildup at Tc. And so here's an example of one of the best known Kagame magnets. A Kagame lattice is a lattice of corner-sharing triangles in 2 dimensions, and the picture, that's where the word comes from, where it comes from basket weaving. And this is an example of this compound strontium chromium gallium oxide has extremely high Weiss constant, 500K. So that if you had the same spins with the same interaction on a square lattice, it would have ordered all the way up here. Okay. Nevertheless, it still is looking like it has good free ion behavior. The slope gives you the moment of the chromium ion, and it agrees with the theoretical value of the chromium. And this downturn is where correlations are happening and it gets lost. But one of the important things is that if you go down to this low temperature region, look at the specific heat. Here's an example. You get about 15% of the total entropy at an energy scale that's 2 orders of magnitude lower than the Weiss constant. This is kind of the nature of frustrated. This is a common characteristic. Okay, so in addition to structural weight downshift, a remarkable feature of geometrical frustrated systems is return to spin glass behavior accompanying very low levels of disorder. And this was a big surprise. So just let me explain what spin glass is. Spin glass has, from an experimental point of view, is a material that has a cusp that's frequency dependent. These are taken at different frequencies. And Anderson basically expressed the fundamental materials requirements, which are a material that has both frustration and disorder. And so in some of the first spin glasses were copper. If you put 1% or even 0.1% of manganese in copper, it'll show this behavior. It's really amazing because I mentioned percolation physics. If the interaction between manganese were short range, that would be well below the percolation threshold. You would not see that. You would just see sort of a rise all the way down to T equals 0. So this is really quite astounding, and it fundamentally originates from the nature of how the manganese atoms interact in copper, which is a metal they interact with the RKKY, which has an oscillatory dependence, and this oscillatory dependence of J on separation between ions combined with the random positions is what's thought to be behind the so-called Edwards-Anderson order parameter. Now, here's some early examples of spin glass freezing with GF magnets. This is the first one by John Whedon at McMaster. He made yttrium-molybdate, pure material, no disorder at all, and saw this amazing, very robust spin glass signature. And he speculated that it was, there's some ideas by, some ideas by Deland back about 10 years before that you could have a spin glass in a pure system. Those ideas are not right. Nobody believes them. So, but that was interpreted in that way at the time. I came along and measured strontium gallium oxide, a slightly 10% diluted sample, and so we're seeing spin glass behavior at 90% concentration, and that shouldn't happen in a regular magnet, but it's a common feature of frustrated magnets, and in GGG, gadolinium, garnet, and saw this. Here, interesting, the disorder in GGG. So these are high-quality single crystals cut from a huge pool, and the reason I have these samples is that GGG was used as a substrate, a non-magnetic substrate for YIG, lithium-ion garnet, and Dell Assets make a lot of microwave devices using YIG, and they sort of grew tons of GGG, which is non-magnetic at room temperature, but at below 1K, it's a really good frustrated magnet. So I probably have most of the world's supply of this stuff. I have huge pools of it. If you need a sample, let me know. But that's, where the disorder comes from is that they found, the guys in building 2 that did the industrial crystal growth found that when they grew stoichiometric DGG, you've got this like weird sort of this weird crystal that people sort of mess up. But they can make a nice, beautiful pool when they put in 2% aluminum. And that's where the disorder comes from.
Sorry, can I ask you a question?
Yeah.
Are there differences between compounds and dynamics and difference in spin glasses and stuff like very long realization times, how long
None of that we can find. We're looking at, right now we're studying realization time, but we look at Chi-3, that's really the main measurement we've done. They all have Chi-3. They all have divergent Chi-3, and Chi-3 is thought to be the susceptibility that reflects the divergent correlations in the water parameter. So the way to think of it so far is that there's no difference between these behavior and conventional spin glass. We've looked, and nobody can find any story. So I just was totally baffled by how this could occur, and I wrote this kind of obscure statement that it's a physically different situation. I didn't know what else to say, but I now know. And we're just talking about a physically different situation. But let's go back to quantum spin liquids just very briefly. Several compounds, and this is taken from one of those review papers, have been identified as, I'll just tell you, one of the ways I got into this way of thinking. They're all in the sort of same class that I originally identified in 1991. And there are a bunch of new ones with lower transition temperatures. But here's an example. This is the first one that was discussed, kappa T, commonly referred to. And this is a specific heat over T versus T squared. This is a standard plot for showing that you have a Sommerfeld coefficient. If this were a metal, this would be the Sommerfeld coefficient. And but never mind that it's not a metal. It was claimed to be a Sommerfeld coefficient and comes from a Fermi liquid. How that can happen in a spin system, you'll need to read Savary balance review to understand how that can happen. But the problem is that this is actually a relaxant. This shows the dielectric constant as a function of temperature at different frequencies. And the problem is that relaxant behavior implies quench disorder. Not surprising, actually, because the ET molecule is the magnetic molecule, not the copper group. And the ET is a free object with free radicals that sit presumably on both ends and lead to quench structural disorder. So this is the sort of mayhem that is just right in this field, that claims based on lack of data. So what is it? It's probably a glass signature, because glasses also have linear terms in the specific heat. So the big question is whether Fermi liquid degrees of freedom can exist, and this is just a flavor for how. I'm not a theorist, so but this is what is being assumed in quantum spin liquids, that you can have a spin operator that can be deconstructed in terms of bosons and fermions. This goes back to the quark. Okay? This is basically quark physics that has been instantiated in the fractional quantum polar pair. And the hope is that these syntheses will also provide the platform for this. So the hope of Parkline constructions that these representations are induced purely formally. If we guess correctly, the Parklines may take life of their own as true quasi-particle systems. Or in other words, wishful thinking. So there are essentially two types of behavior that can be observed in frustrated systems. One of a kind can either go up or can go down. When it goes up, it always becomes an antiferromagnet. When it goes down, it almost always becomes a spin glass. This is a kind of reduced scale with a whole bunch of different compounds, different interaction strengths, lattice symmetries, spin sizes. And the general trend is that disorder induces this type of behavior. It's not surprising since it's a spin glass. So we're going to try to understand disorder. The first question is, what are the degrees of freedom? The first attempt to identify the degrees of freedom was the so-called orphan spin model, and which was a very simple idea promoted by my former postdoc, Peter Schiffer, right after he left me. And it makes sense. I mean, if you don't, just looking at the data, you can see that it looks like a line plus a deviation. So you model that since this is inverse pi, that deviation has been added, an added part of the susceptibility. So why not call that added part into a set of spins, calling them orphan spins? Spins that are not, for some reason, are not connected to the rest of the spins. So this is, so you write in this thing, you write 1 over pi as a sum of two, you write pi as a sum of two independent contributions, orphans and background spins. And you assume they're independent. Okay. So the problem with this interpretation, and that is that the numerics don't work out. If you ask, okay, how many spins does this represent? It's impossible to relate that to the chemistry of how many defects you put in, which doesn't seem right. And so this quantitative problem is solved by so-called GOES, or what we call quasi-spin model, and in which it was shown by Messner and folks that a vacancy, a spin vacancy, so in the systems I'm talking about, that are usually tetrahedra that are connected by at their vertices, a vacancy here will cause a sort of shielding effect among its neighbors, and from far away this will look like a type of spin, not an atomic spin, but one that has a somewhat reduced moment half, something like that. It's probably So now let's look quantitatively at the difference between conventional spin glass, such as europium strontium sulfate and nickel zinc gallium sulfide. If you plot chi versus a reduced temperature, T over Tg, Tg being the glass temperature, you can see that as you put in more europiums, the signal goes up. Not surprising, right? You put in more of what you're interested in. Same thing with nickel gallium sulfate. No, actually, different thing. As you increase the density of non-magnetic ions, so the quasi-spin that I talked about, the signal goes up. So it's the same sense, only you're not talking about atomic spins, you're talking about composite spins. So this brings the focus now on Tg, the collective energy. What controls its magnitude? In conventional spin glasses, it's an intuitive result from a mean field perspective. Tg increases with increasing spin density. So this is what the data look on a non-normalized scale. This is taken from the Red Felt, a very old paper, and this is all very intuitive and as expected. So for GF systems, it's not unreasonable to suppose that since disorder, which we'll just call delta, is proportional to the density of spin vacancies, that Tg should go like the density of spin vacancies. Or in the context of the dipolar spin glass, as considered by Rosenetz and Senn, Tg should go like x, where x is the vacancy density. So one would expect to see, when replotting this data on a non-normalized scale, something like this. That's what we would expect to see if this were like europium strontium sulfide conventional spin glass. Instead, what we see, and so this can be expressed as d chi at Tg dTg is greater than 0. That's not what happens. Instead, this is what happens. So the collective energy goes down, and the signal goes up. Okay? I've known about this sort of data for a long time. I'll show you the original data. So this is what the two. So this is a difference that you don't have to know anything about the physics or the materials or anything, but you can tell that these are two qualitatively different behaviors. This has been bothering me for almost 30 years. Actually, since this paper appeared. So this is the first demonstration of this by Oberdorf's group, showing in this cadmium system that as you put in vacancies, the signal goes up. Right? So that confirms the quasi-spin idea, but the collective temperature goes down. What got us into this recently is a few years ago, we were looking at this iron tightening system diluted with non-magnetic gallium, and we saw the same thing. So talking to my colleague Sergey, he said, "Well, that's odd." And I said, "Well, that's what you see. And all systems, no one understands it. I don't understand it. So let's understand it." So he got me to plot up all the data I could find. So this is, if anyone can find more systems where I can put on the slide, I would appreciate it. But this is all the data I could find where systematic studies of the susceptibility with the concentration of magnetic ions with it. All of the conventional spin glasses show this behavior, which is the intuitive behavior. All of the geometrically frustrated systems show the opposite behavior. Stare at this for a while. I should make this animated, but it's, you can see it's all the same. Here the susceptibility is dimensionless. But let's relate it to materials components. So here I'm going to plot Pg versus disorder, or the nominal vacancy concentration. And you can see that all the data went here. So this is where, at this point, Sergey said, well, that implies that there's an energy scale in the pure system. Right? It's sort of obvious. Now, the reason this had not occurred previously, that this logic, this train of logic had not occurred, is that the whole community, literally for 30 years, thought that all of the spins were involved in the spin glass state. And there was no requirement to calculate what the freezing temperature was, because no one can calculate that for regular spin glass anyway. So it was just this big cop-out. And everybody assumed that all the spins were in the spin glass state. And we know that cannot be true, because in the pure system, there's an energy scale. And that energy scale is sort of geometrically between device temperature and kind of the lowest interaction energy in the system, the dipole interaction. But this is a feature of the pure system, and that's ultimately what we're interested in because we're interested in pure behavior. I mean, let's figure out the pure behavior first before the disordered behavior. So the observations are that the hidden, we call it the hidden energy scale T star, the property of pure material. This is the materials limit in which quantum coherent magnetism is being searched for. And all known data are consistent with the freezing degrees of freedom induced by spin data. In other words, they're composite spin.
So none of this material is older down to the lowest level.
In fact, I took off from the original data, I took off a couple of compounds that do. Zinc chromatus 1, for instance, that actually orders and then has a spin west temperature. Anyway, this is a complication, but all these are non-ordering.
Could you remind us what the horizontal scale is? How do you define QG if there's a spike?
You just measure it. You just measure it.
No, I know, but what is there a maximum?
Yeah. Of course, it's slightly frequency dependent, but when you get down to these, it becomes really hard to actually see the signal at some of the, for some of these systems. But it's at a finite temperature, it's not a zero temperature. Okay, so we're interested in behavior of pure systems, and you might be surprised that people have done a lot of measurements on the pure systems. One of them is neutron scattering. And so this shows, so you might say, well, what are the things doing at this energy, at this temperature? And so here I plot on a reduced scale now the susceptibility for strontium chloride gallium oxide, the cognate system, and the elastic neutron intensity at a short wavelength. So this measures, so there's no long-range order, no Bragg piece, but there's a broad background that characterizes the magnetic short-range order and follows this temperature dependence. Just the fact that you can see this in neutrons means that it's probably due to the bulk of the spins. So that's strontium, chromium, gallium oxide. There it is on our phase diagram. Here's nickel gallium sulfate. Here's yttrium molybdenum oxide. So Tagamate spin 3 halves, triangular spin 1, pyrophore spin half. Yeah, I think spin half. And this actually, so this is spin 5 halves. But it's a structure called the pseudo-Brookite structure. But the triangles aren't easy to see, but it's nevertheless extremely frustrating. And this shows the same behavior. So these are all the data I could find. Okay? So clearly the founding microscopic characteristic of geometrically frustrated systems is the development of short-range order in the pure limit and at the hidden energy scale. So
are these all empty or manufactured?
What?
Are these all empty or manufactured in all the three systems?
Everything is from. You can't have frustration without any from answer.
So when you say development of short-range order of pure systems, so in a spin glass, there's no average order, but you have well-defined lines or moments locally everywhere. So are you saying that in the pure limit of these models, that you would actually find something like that, like a random non-zero spin texture at zero temperature?
In the pure limit of what?
So in the pure limit of the new compound,
well, yttrium molybdate is stoichiometric, so is nickel gallium sulfate.
Right, but especially in glass, there's some randomness.
There's some randomness, there's randomness that is most likely typical in oxide. It's just that we have an awesome impurity detector, and I'll show you why. It'll become apparent why in just a few minutes, okay? Even for like so how is a material made? I mean, you make materials and you look for another phase in the X-ray diffraction. That doesn't mean that what's left has no disorder, right? There's all sorts of ways that you can have disorder very subtly, right?
How pure is pure?
That's the whole question. I mean, it's not the whole question. I think you won't be asking that question at the end. Okay. But that's certainly one of the things that I would hope that people do is make more pure materials. But no, we don't know how pure is.
Silicon is
Exactly, and so silicon can be made at ppm levels of purity. These materials are probably at 1% or slightly under 1%, or 0.1%. But bear in mind, you can get spin glass behavior in copper manganese, I think with like 0.001% manganese. It's hard to measure because it goes down to very low temperature. But it's that long-range interaction. That's the thing. Yeah, I'm gonna get there. That's what I said, the long-range interaction. So how does this happen? We'll get there. Okay, so neutrons are great for seeing what the type of order is, or short-range order, but they can't count the spins, right? I mean, it's hard to actually count the number of spins, right? You can do it, I think, but it's hard. But specific heat is famous for counting spins. You actually count the number of degrees of freedom, and if you can isolate the magnetic. So this is a work in progress. Sorry for not having all the data here, but this shows you how under-investigated these materials are in some ways. The only one for which we have really good specific heat data is nickel gallium sulfate, primarily because its vice temperature is only 100 degrees. All the others have much higher vice temperatures. So Nakatsuji measured this, thank goodness, and he gets almost all the entropy in two peaks, one around vice theta and one around this low energy, this hidden energy. So this isn't even the whole story. There's a lot of entropy loss. There's a paper on copper gallium oxide, copper gallium, which claimed, based on measurements only done up to this point, that there was 0-point entropy. But I measured it up to higher temperatures and recovered the entropy. So we need more measurements here, but it's looking like that this hidden energy scale represents the loss of the majority of the spin entropy on cooling. So the interaction must be long-range if it's showing spin glass behavior at arbitrarily low temperatures. How does this work? Well, in copper manganese, in canonical spin glasses, you have an interaction. It exists independent of whether the spins are there or not. It comes, sort of kicks into action when you put spins, but the conduction electrons are there. And when you see freezing, it's a competition between the average strength of that interaction and the thermal energy. And that's when the thermal energy becomes less than the interaction energy, then you see some sort of freezing. Here the situation is quite different. Above the short-range order, you have paramagnetic, and below the short-range order, these spins are now talking to each other. So the interaction is a function of temperature. The interaction, the permeability, is a function of temperature. We call this the Eminuscent phase because Eminuscent is Latin for long range. I'm just going to call it that. And what determines the hidden energy scale? So the naive explanation is the presence of non-vacancy disorder. That actually occurs in neutron liquid. That's another story, but it's unlikely to explain the other systems. We know why it occurs in neutron liquid because liquid 4+ had a non-polar interaction, but that nevertheless it still has the same behavior when you put defects in. Spin freezing in the absence of disorder, I've already discussed this, but it doesn't really explain the data. But the geometrically frustrated medium undergoes a sharp crossover at T star, the properties of which drives spin glass freezing. Let's explore this scenario. That's the one I just depicted in the cartoon. So what are the key properties that theory of geometrically frustrated systems must incorporate? Obviously, they have to have interaction. Thus, they try to minimize the internal B field. They possess no long-range order. They're highly degenerate. There are long-range correlations among defects. This situation suggests a Coulomb representation description. And Chris Henry wrote a great article on this in 2010. Fortunately, he's not with us anymore. It's often called the Coulomb phase, which we believe is a misnomer because there's no phase. It's a representation. Instead of talking about the spin that is degrees of freedom, we talk about monopoles and dipoles and so on. Okay? So what's an example of the usefulness of the Coulomb representation? Well, there's this experiment on specific heat of spin ice, dysprosium tightness, which I did in 1999, And what I showed was that you just measure dysprosium, this is the dysprosium, spin at half degrees of freedom that are freezing. I should mention that all the other rarer titanates exhibit a nice sharp ordering peak in the same energy region. And at first I was concerned that the sample was somehow, they were made by Bob Cobbin, so I had to ask Bob, are you sure the sample is any good? Because it really doesn't look like the others. And she assured me that it had the exact same X-ray diffraction pattern. And so this shortfall of entropy is extremely close to Pauling's ice entropy, which you know what ice is. Ice has a perfectly ordered oxygen lattice, but the hydrogens are completely disordered. It was a big problem back in the 1930s, and Pauling solved it by showing that there was just this exact type of that there was a degeneracy. Hydrogen could be one of two positions, close to or far from an oxygen. And that's basically the Ising model for spins on the particle lattice. So the Coulomb representation for spin ice assumes coarse graining on length scale greater than the tetrahedron and magnetization density of beta C then equals 0. The key property of spin ice is that at low T, where the ice rules enforce energetically, the entropy is defined. In the Coulomb representation, degrees of freedom aren't stated but monopoles dipoles, loops, and photons. The main quantity in the Coulomb representation, the magnetization density, and its associated degrees of freedom. And one of the key relationships, at least for me, is that the entropy goes down as the magnetization goes up, which is the opposite of what happens in an antiferromagnet. If you put a field on an antiferromagnet in its ordered state, the magnetization goes up, obviously, that has to happen. But the entropy goes up also. Because what you do is you transfer the degree of freedom, as you say, it's more entropy. So this is a testable, thing. It's already been tested. I'll show you. And so another important aspect that the Coulomb representation mediates long-range interactions, which are evident in the Eminuscent phase. This is an idea that's been out there. It's been called the entropic interaction. And it's just a feature of the type of short-range order that is similar to the 2 in 2 out state of the spin ice. I forgot to say what the entropy really was in spin ice, but this entropy comes about because the lowest energy, so not a great picture, but the lowest energy state energetically is 2 in 2 out, but there are multiple ways of doing that. And that's the source of the entropy. Spin ice, very similar in water ice. Okay, and this shows the field dependence of the entropy in dysprosium titanate. As you can see, it goes down when you put a field on it, as Henley would say. Ultimately, you get more entropy, and this is a plot that convinced me that this was a spin ice compound. Okay, so what are these excitations in sort of our state, our systems that are responsible for this degeneracy? So now I'm making a distinction between spin ice, which is all ice with no sort of non-icing version of spin ice, but all the systems I'm talking about are non-icing or vector spins. So suppose we have a state, one of our Eminuscent state systems, in this frozen into the state I've projected on a 2D plane here, the version of the ice state for the Coulomb representation. So we can rearrange the configuration by flipping one spin here, and we make 2 energetically unhappy tetrahedra. But if we flip another spin, there's no overall cost. Likewise, when we flip another spin, and likewise when we flip the last spin, we get back the energy. So this is an example of how of the type of excitation that one might form. It's sort of analogous to a Goldstone mode, but it's not. It's restoring a different type of symmetry than in a Heisenbergian ferromagnet. So this is an example of that entropy that is being lost below the peak in specific heat at the hidden energy scale. I think I'm almost done, but I don't know what the time is. Okay. So So what's the implication? Hidden energy scale. So if there's a wrote out the free energy, we want to, for the undergrads, F equals U minus TS, right? Everybody knows that. So we have the internal energy through the B field and the entropy that we just discussed. And find the free energy. We put in a whole bunch of other terms. Forget about these terms. These are just terms required for a Gaussian field. Let's focus on this one. This comes from the U minus TS. So that term here leads to a permeability that's temperature dependent. So if you think about it, if anyone knows of a system where permeability is temperature dependent, please tell me. But it makes perfect sense because the interaction is being mediated. We know the interaction is being mediated by a bunch of spins whose behavior is temperature dependent, right? So it makes sense that the U is temperature dependent. But I believe this is the only instantiation in all of physics of this effect. Okay, so once the connection between quasi-spins and background spins is acknowledged, one can write down a different form for this accessibility. So instead of the orphan model where these two terms, the background and the upturn, are independent, we make them dependent, as you should be, right? Because if you take spins, if you put vacancies in, then you're taking spins out of the background. And so the simplistic notion of what's happening is that what's controlling the collective degree of freedom is basically a perforation phenomena of the short range order in the pure system, but what's controlling the size of the signal is the number of spin vacancies. Okay, so at some point, someone might ask, well, what about Hilbert-Smith? That's one of my esteemed referees said. Because Hilbert-Smith doesn't show a spin-glass transition yet. Everybody believed at one point that it was a quantum spin liquid. Okay, so the point is that the Coulomb representation in 2D does not admit you can find charges. That's another way of saying that the Eminuscent phase can't form in 2D. So we identify the Eminuscent phase by the spin glass CG. We do not have the same spectator role in 2D systems because, as I said, 2D systems don't show spin glass freezing, and this was actually addressed as recently as 2016 by a group including Parisi, where they did this massive computation and could find no evidence for spin glass freezing. Peter Young, our local expert, as well as Steve Kippleton, also confirmed this. If there's something that can't be analytically proven, then you have to rely on sort of best est. However, field-dependent analysis of a specific key for Hilbert-Smithite shows scaling behavior that can be modeled perfectly instead of in terms of what they call random singlet states. So these would be random, sort of frozen random singlets. Random meaning that the singlets can encompass a random number of spins. And in the original Hilbert-Smithite paper, there was a neutron scattering plot. I couldn't find any successive data, but clearly the short range order at short wavelength in Hilbert-Smithite. So that shows that the short range order is developing, okay, which I'm taking as evidence of lack of entropy and therefore inapplicability of all spin glass, of all quantum spin liquid theories. So what are the implications? So while I limited the discussion to those materials with F, the frustration ratio greater than 10, all the statements I'm making are generic. And please correct me if you see anything wrong. In this class 3D, in 3D, the Coulomb representation of physics justified introducing long-range entropic interactions, which allowed us to make sense of spin glass freezing on very loose quasi spins. In other words, spin vacancies while 2D node spin glass transition exists. We still see signs of short-range order and disorder. But this means, apart from the effects of disorder, there's an even bigger problem for QSLs, which is that all the QSL theories are done at T to 0, and other stuff happens between J and 0. So let's end on a positive note. I view this as really the start of quantum magnetism because we now understand what the problems are, at least in a framework way. But it leads to this, I think, is only a short list of if you like to pick up this morning, of the problems that data leads you to thinking. So we clearly need a microscopic theory of Schrödinger's order. What determines that hidden energy scale? That's a huge problem. There's clearly an energy scale in a condensed matter system which we have no idea the origin of. Okay. There's a whole bunch. I'm not going to go through the whole thing. You can read them at your leisure. I'll just highlight a few. The state will have a random internal field at a length scale L greater than A. Can a quantum coherent state among the residual degrees of freedom exist in such an environment? That to me is the biggest question. What are the principles governing the universal behavior of geometrically clustered magnets? It's one of singlet formation and their interaction. So there are principles. There are principles involved here. It's not just a conclusion looked at from a bunch of data, right? The spins are doing something. And the reason I say this is because there's a whole slew of new materials with interaction energies that are order of magnitude or more or less than the systems I'm going to show. They involve rarer things. And the physics changes the origin of the interaction. You have dipolar interaction, you have field complication, but there are principles involved here, and the principles should tell us whether these systems, these newer systems, are developing the same sort of density of singlets. Spin singlets appear in other systems, for instance, dimer solids such as barium chloride, plateaus such as serum and timonide, and many others. Someone showed me some more plateau systems. What role, if any, do they play in the triplet ordering, or are they the dark matter of condensed matter physics? That's something I like. Can we measure these permeabilities were measured back in the 1700s, right? We learned how to measure permeabilities. I haven't thought about this enough, and it's probably beyond my expertise. So anyway, it's not the end, but the beginning. Thank you.
So I mean, I still haven't understood. So what is the case difference between American and Eminuscent? I mean, what we should use is all this sort of principle in case of I mean, there's no architecture why, right? In case for Eminuscent, where all these sort of forms.
Yeah, but there are insulating conventional systems. So the insulating, like Rosen's strong profile, is a conventional spin-glass. And it is not light weight. It shows the spin-glass degree around circulation pressure for 3D. And that's presumably why spin-glass.
I mean, in principle, one can sort of solve this problem if you know whether the really going the wrong way. You can basically completely polarize the system. Making it into a polar margin, looking at the excitations of those. If those are, excitations are sort of shown in order, you then can expect excitations to, not to be limited, almost including two freeways. Whereas in the case of glassy case, as in the case of the Smith side, and all these determined maybe all this other stuff, when you polarize it, you see spin excitation is basically not to be limited. I mean, the actual potential.
You might want to do that sort of measurement. You might want to do on a geometrical project, and then one which is chemically similar, like Ramirez on solar, right? Because those the nature of the interaction is both are short range. The two body interaction is short range. So you've got some similarity there, but the difference comes in that the geometrical project system will have this property interaction. Open property will not. So that's the experiment.
So the experimentals have always
We're trying to turn on a light.
well, I don't know if this is working or not. So I'm always a little bit allergic to arguments that sound a little too close to like theological interests and that thing.
Well, show them.
No. So how should I think, so that's a preface, so how should I think about it? Imagine that I could make a truly pure material, like perfect work, as
That's why I say the disorder is kind of like a distraction. It's a speculator. It's slave. It's subsidiary to the short range order.
I guess I'm trying to understand, this is for all of us, I'm trying to understand how, if I don't have these, kind of vacancy, kind of composite objects that are interacting with each other through things like, the monopoles or whatever you want. If I don't have any of those, you're saying I'm still going to get dependency for a short range order.
Definitely. No, not
And that's
you'll get short range.
I will get range order, and that short range order will kick in at sort of essentially infinite temperature. It'll be at the end, slow
Well,
enough.
two, but I did a hint actually the future. It's actually two steps. And one is you get some short range order at jet device temperature. You lose 30% of the entropy it gets. That actually, and then you lose the rest at the storm. So it's really, there's no entropy left. This, by the way, has been modeled by IF. Here at Cornell, he modeled Dennis Rabel results of field 3 on graphite at a concentration that corresponds to plasma environments, so Dennis saw 2 pieces with 2 peaks, and light gets the same 2 peaks in a finite size exact concentration. So we're actually expanding that work of light, which is back to 1999, and trying to show how that we think it's more universal.
Sort of. So when you say short range order, I'm just trying to understand exactly what you mean. So, I mean, you could be above ferromagnetic transition, and if I look at a short range correlation function, I will see short range order.
No, that's not what I'm talking about. I'm talking about zero field gain ferromagnet.
Right, so you're saying actual non-zero moments at zero temperature, so like a frozen spin temperature.
Yeah.
Magnetic.
Happens all the time. For instance, it happens in low magnet. If you look at the sophisticated class of laser magnet, it'll look like there'll be a broad peak, like a quasi 1D or a quasi 2D magnet. There'll be a broad peak, and then a little blip where the change of the plane work. That big peak is the short range order. So it's trying to order that it can't become fluctuation. Here, it's not fluctuation, it's something else that's presenting.
Right, but so I guess theoretically, though, your claim then would be that if you could do the honest calculation of finding the Brown state of a Heisenberg with however many couplings on a pirate form, you're actually not going to find still with the Brown state, you're going to find.
Yeah, I'm 100% sure of that.
We're keeping it in the pure system.
Yeah.
There's absolutely no
Yeah,
disorder.
no, because the cities do something else. They do something else. They don't go to T equals 0. They form singlet first. It's in the data. It's in all the data that I did show that. You need to pick what data it is. But there's no violation of anything that I said today.
Rose,
I think you already mentioned
Oh. I'm not sure I can explain that. So if you measure, so I can just explain that from an experiment. If you measure this hysteresis, because if you cool it down in 0 field, apply a field, and then take data going up, you'll see it. But if you cool it down in the same field, then that peak, you'll see something, but there'll be a big hysteresis between the data below PG taken in 0 field to the field. That hysteresis implies frequency dependence. I don't know how else to explain it, but
I guess the only other way that I could think of explaining is that the spin glass freezing is non-thermodynamic phase transition, so it's not equilibrium, but rather a dynamic feature that signifies the presence. Dynamic means time dependent. And so the frequency is the frequency of the magnetic field that you're using for the measurement. So the freezing of the spins changing depending on how fast you're forcing them with the field.
the order parameter is actually, if you look up Edward Dennis' order parameter, it's a time correlated just like, so you and I don't feel bad, nobody will understand.
So I feel that the road control can never with a specific so what we know that
Sorry, in what system, or you about the system or just general?
In general, physically, we can only measure how much we can get.
If then it's labeled, then it's feeling beyond that, it's really tough, it's only really tough. So we can feel that. Yeah, so what's the question?
there are some conditions that below like you know
Right, but I guess what I'm saying is that if all the entropy is gone, then how, what sort of illustration are you talking about?
I mean, there's no entangled space, right? That's the claim.
I mean if there's
No
some
entropy is what I'm saying.
if there's some condition like where close to like where no energy so there's no way you can see from that
You feel the entropy. There's a key square behavior principle in calculus. I didn't dwell on it, but the statistics of my key square. The key is that there are spin wave-like objects, and perhaps those can be shown to be coherent in some level.
I mean, you don't think communication how to actually your data something. But you got the
Challenge for the young generation.
Can I ask you a quick question? So, in order to tackle it, I'm not going to speak about it. I don't think Oxford Dictionary knows what Eminuscent is.
No, it's a new word.
So what does it mean and where did it come from?
It means it's a phase that mediates moment interaction. It comes from the word Eminuscent. But then we also consulted with our local Italian expert who, after physicist, Stefano Fumo, who took 4 years of that. He said, well, we should call it Eminuscent.
And Eminuscent stands for, like, what's the
Long range,
long range.
yeah, long range math. And then he was right.
Yes, what we learned is that there's no longer in order to Thank you, Art.
I googled it once, right? But all it has is geometrical, what it says. You know what I said? Instead of peak, right? So there was no line. I even looked like that.
I googled long range in Latin, Eminuscent. No, if you Google long range in Latin, you get Eminuscent.
Well, I just
It means from the hand, right? Away from the hand, long range.
So, what if roller signals
We don't know. It's a big question. It's a really interesting big question. And there are other systems where singlets are really, I think singlets are playing a big role in plateau.